continuing full force. So currently, Jingfeng is going to tell us a little bit more about some of the research that is going on robustness side. If you have
Thank you. I'm really happy to be here to present my work on application of adversarial robustness. I'm in imperfect information learning team with Professor Sugiyama. Let's talk about. I'm going to cover two aspects. One is background knowledge of adversarial attacks and training, and also I want to cover two case studies on how to apply the adversarial robustness. Let's go to the point one. We know that adversarial attack can evaluate the vulnerability of machine learning models because machine learning models are sensitive to the input perturbations. For example, with only small noise, the image of pig will be wrongly recognized as the airliner. How to construct the adversarial data? We basically solve a constraint optimization problem. Given an machine learning model and its loss function, we output the adversarial data, maximizing the loss within the non-ball constraint. The non-ball constrains the same semantic meaning between the natural data and the adversarial data. The epsilon controls the size of the non-ball. Project gradient descent, PGD, approximately solve the constraint optimization problem. Given a starting point, PGD calculates the gradient of its loss function respect to the input. Gradient is a direction pointing to a place with a slightly larger loss. Now we get a new point whose loss is slightly larger than the natural data. Then we calculate the gradient again. The loss of yellow point is again larger. So on and so forth. Finally, we get a red point with the highest loss, which can make machine learning model inaccurate. Why machine learning models are so vulnerable to the adversarial attack? It is because the standard training output a model whose decision boundary is near the data. Therefore, when we slightly perturb the near decision boundary data, the model will make mistake. Even worse, due to the curse of dimensionality, almost all data are near the decision boundary. To meet the above challenge, we have a new learning style that is adversarial training. The adversarial training has two purposes. First is to correctly classify the data, that is, increase the natural accuracy on the natural test data, which is same as the standard training. Second, unlike the standard training, the adversarial training output a thick decision boundary. Therefore, the data are encouraged to be further away from the decision boundaries. The learning objective of the vanilla adversarial training is a minimax formulation. Inside, there's a maximization where we use the PGD method to generate the adversarial data. Of course, we can use a new method, DT. This is more fantastic. Outside, we have a minimization where we can use a classifier to fit those generated adversarial data. To realize this learning objective, we can use the alternating optimization technique. At each epoch, adversarial training conducts step 1 and step 2 alternatively. Step 1 is to generate the maximizing loss adversarial data, commonly using the PGD method. Step 2 is to minimize the loss on those generated adversarial data. In comparison, at each epoch, the standard training only minimizes the loss on those natural data with respect to the model parameters. Now I'm going to talk about how to apply the adversarial robustness. We know that adversarial attack is a way of uncovering the vulnerability of those machine learning models. And adversarial training is a way of making those machine learning models robust against those vulnerabilities. Next, I'm going to show two case studies using attack to evaluate the vulnerabilities and using adversarial training to enhance the adversarial robustness. Image denoising is to reconstruct the clear image from their noisy observations. Therefore, it is commonly used in medical image, satellites, or cameras. In image denoising, the noise is generally considered to be a random variable with zero mean. For example, if we take a large number of pixels and compute its average, then the noise should be cancelled out. Otherwise, the noise will affect the brightness of the image, will not be considered as a noise at all. Because of this zero mean property, the traditional method in the OpenCV package using the non-local mean denoising. The idea is simple. Given an image, we find a similar patches and then compute its average. Then we can average out the noise. Now we go to the machine learning time, and we need to learn a good image denoiser. Specifically, the image denoiser is denoted as a deep neural network, taking input the noisy images and giving output the clear images. However, in practice, we only have clear images as the training data. To solve this, we construct the noisy images by adding Gaussian noise with zero mean of various levels. Then we can learn a deep image denoiser that performs much better than the conventional non-local mean denoising method. However, although the deep neural network has good performance, it is vulnerable to the adversarial attacks. Similarly, this also applies to the deep image denoiser. To explore this, we ask a research question. What kind of zero mean noise that can make the deep image denoiser fail? To answer the above question, we designed the zero mean adversarial attack to evaluate the vulnerability of those deep image denoiser. To realize this attack, we use the PGD method. But this PGD method has two constraints, which is different from the conventional one. First, the noise should meet the zero mean, but the bounded by the adversarial budget. Second, the noise should meet the zero mean property budget. To realize this, we customize the projection function pi in the PGD method to meet the above two constraints. To meet the zero mean property, the projection function pi should project the adversarial noise onto the zero mean plane. The zero mean plane consists of all vectors whose mean of the element equaling 0. How could we project a vector delta onto a plane? First, we find an O1 vector that is orthogonal to this plane. Then, we project the vector delta along this direction of this O1 vector. Then, the adversarial noise delta minus this new projection leads to a new vector, that is black one, that is on the zero mean plane. Some mathematical tricks. Now we have our two steps projection pi. The first step is to meet the zero mean constraint. The second step is to meet the adversarial budget constraint, epsilon. For example, the deep image denoiser can effectively handle the normally noisy image and remove the noise to reconstruct the clear images. By comparison, if the noise is crafted by our zero mean attacks, the performance of deep image denoiser is severely damaged. we can see some blurs remaining on the roof and some strange contours appearing in the sky. Therefore, our zero-mean attack can indeed uncover the vulnerability of the deep image denoiser. Then, can we make the deep image denoiser robust? The solution is adversarial training. We add an additional loss term to encourage the output of the noisy, non-adversarially noisy images to be similar to the output of normally noisy images. Therefore, we train the deep image denoiser using both adversarially noisy images and naturally noisy images to ensure that the reconstruction quality is high and the reconstruction is robust. To realize this learning objective, we alternatively use the PGD method to generate the adversarial noise, and then to minimize the adversarial noise by using the above two loss functions. Then, compared with the standard training, our adversarial training can ensure the reconstruction qualities under attacks. Last but not least, we surprisingly find the robustness of deep image denoiser can also benefit the generalization capacity on some unseen real-world noise. In other words, the robust deep image denoiser can denoise some real-world noise even without training on those real-world noisy images. We guess it is because adversarial attack can exploit some worst-case noise. Learning from those worst-case noise can make deep image denoiser deal with various types of unseen noise. Let's look at another example, two-sample test. Two-sample test is a statistical hypothesis testing, judging whether the two sets of samples coming from the same distribution. It is widely used to analyze the critical data in physics, chemistry, biology, so on and so forth, to check whether their scientific experiments had made significant changes or not. How to test? We first define a test statistic. L. The test statistic measures how different the two batches of data are. Then we compute the p-value. P-value is the probability of observing this value of test statistic given the norm hypothesis that the two distributions are the same. If this p-value is very low, we reject the norm hypothesis. Let's look at a simple example. T-test. For example, we have two batches of apples of various size from two companies. We want to know whether these two batches of apples have the same quality. Then we calculate the t-test test statistic of P and Q. Bar XP is the average of these 5 apples. XQ bar is the average of these 5 apples. Sigma P is standard deviation of these 5 apples. And sigma Q is standard deviation of these 5 apples. NP equal to 5, NQ equal to 5. Suppose we get the value of minus 2.44. We want to know this value is large enough to tell those two batches of apples are different or not. Then we're going to calculate the p-value of this test statistic L. Then we look at the probability density function of the t-test. We find two side of p-value here, the probability mass here. We look at the table. The probability of the test statistic larger than 2.44 under the null hypothesis seem to be very, very low, then it's an unlikely case. Then we're going to reject the null hypothesis and conclude that the two batch of apples have different qualities. In reality, a t-test is very limited, which cannot handle the complex distributions or complex data. Therefore, we commonly use the general purpose test statistic. However, computing quantile under the complicated test statistic is tricky under the null hypothesis. T-test, we have a table to look at it. For the general test statistic, we do not have a table to look at it. How to do this? We're going to use the permutation test. They have 3 steps, and they repeat these 3 steps. First, under the null hypothesis, we randomly shuffle the joint set of SP and SQ into S1 set and S2 set. Then we can treat S1 and S2 coming from the same distribution. Then we compute the test statistic of S1 and S2. Then we repeat. For example, suppose we repeat this process 1,000 times, even 10,000 times. Then we can plot the empirical CDF of the test statistic under the null hypothesis. Finally, we can locate our test statistic of SQ and SP here. Then 1 minus this value is our calculated p-value of the test statistic SP and SQ. Now, I'm going to introduce a general purpose test statistic, maximum mean discrepancy, MMD. MMD measures the differences between the distribution of P and Q, which is the largest differences in expectation over all mappings, all functions. However, in reality, we only have a limited data. We must restrict the function class, curly F, to provide the useful finite sample estimate. But we also want function class to be rich enough to become flexible. Therefore, we choose the function class, curly F, to be the unit ball in the reproducing kernel Hilbert space, RHS. Then we define the kernel mean embedding to embed the distribution into infinite dimensional feature space. This can allow us to compute and manipulate the distribution using the kernel functions and using the dot products. Then, due to the reproducing property of RHS, we can make the soup dispairs and using the kernel to manipulate the two distributions. Then if the MMD equals 0, the two distributions are the same. We actually can use many different estimations to estimate the MMD. Let me to make the notation simple here. We use the MMD square head to denote one estimation, which can be parameterized by theta and using the kernel K. Then how to test using the MMD? First, we fix a kernel. For example, we use a Gaussian kernel and fix its parameters. For example, inside the Gaussian kernel, we have some low scale. We can fix it. We just manually choose a figure, a number. Yeah. Then, given the SP and SQ, we calculate the MMD estimation. Then we're using the permutation test to calculate the p-value of this estimation. Lastly, if this p-value is too small, we reject the null hypothesis Otherwise, we accept the null hypothesis. Now, we go to the machine learning time. We should learn the kernel parameters from the data. Then we can use the deep kernels. The theta are parameterized by a deep neural network. Then the question is how to learn the parameter theta from the data. We first split the data into the training set and the test set. Second, we define a learning objective and optimize the deep kernel and learn the kernel parameter theta. Then we conduct the normal two-sample test using the optimized deep kernel on the test set. Then the next question is how to define the learning objective. The learning objective is the test power. The test power is the probability of correctly rejecting the null hypothesis when the alternative hypothesis is true. Then, due to the asymptotic of MD under the alternative hypothesis, we can use some central limit theorem. Then the R is the rejection threshold decided by the permutation test. Big theta is a standard normal distribution, CDF. Then for the reasonably large N, the test power is dominated by the first term. Then this will vanish and disappear. Then we can compute this first term using the kernel operation, which can be parameterized by the theta. Finally, we can optimize the deep kernels by, for example, using the SGD, ADAM, by maximizing the test powers on the training data. Then we have the kernel with optimized parameters. The two-sample test with the smart kernels will have a very good testing abilities, which can handle the complex distributions. Okay, now we consider a potential risk that can cause a malfunction of the non-parametric two-sample test. To this end, we use the PGD method to minimize the test power on the test data to search for the adversarial pairs. For example, we have lovely images of cats and dog hairs. The non-parametric two-sample test can correctly differentiate these two batch of cats and dogs coming from the different distributions, which are correct. But if we add some small noise, almost all the two-sample tests will wrongly judge the adversarial pair. They think they can come from the same distributions. So this technique can help you to manipulate the data and change the significance of your experiments in biology, chemistry, even in physics. Looks scary because now parametric two-sample tests seem to be a standard in judging the significance. Then, to robustify the non-parametric two-sample test, we propose to adversarially learn the deep kernel. We want to learn a robust kernel. In particular, this defense is formulated as a max-min formulation that shares a similar taste of adversarial training's minimax formulation. For its realization, we use the training data to interactively generate the adversarial pairs by minimizing the test power, and then update the deep kernels by maximizing the test power on those adversarial pairs. Then we can learn the robust deep kernels. The robust deep kernels will have a good testing abilities, but also resist against adversarial attacks. Let me conclude here. Traditional methods have limited performance. Now we go to the machine learning times, which the models could have a very good performance, but are vulnerable. In the future, we really need those robust machine learning methods, which can have good performance and are also robust against various types of attacks. Thank you.
I really liked this, this evaluations of, let's say, the two sample tests and their adversarial robustness. So you mentioned that you could robustify, and there you said that you train a robust kernel.
Yes, the standard kernel used by the previous research and methods are not robust against the adversarial attacks we designed. Then we show this phenomenon, and then we provide the very first solution to train a robust kernels. Then they can resist attacks.
So maybe I'll catch up with you on the poster session and talk a little bit more.
Sure.
Any questions? Oh, yeah.
Thank you for interesting talk. In the first part, you introduce how to say
denoising.
Denoiser. Yeah. So is the robust denoiser can the robust denoiser be robust to how to say new types of noise? So here you use your proposed attack, right?
Yes.
But how about other attacks, other possible attacks?
Right now, we propose some zero mean adversarial attacks, and we show that this method can resist against the zero mean adversarial attacks. There could be always some attackers design some, for example, the patch attack, or other some pepper and salt attacks. Then our method may not handle that attacks effectively. The philosophy behind this is security is always arm race. The party who have more knowledge will always win.
Thanks for your talk. Okay, I have a question that so just now you mentioned you want to train a robust kernel because the previous kernel are not robust. So could you please emphasize how do you introduce some robustness regularization or something to introduce to train the deep kernel?
Yeah, for example, in the standard way of training the deep kernel is maximizing this loss term. This is only one step, kind of like a without looped optimization. We can change this optimization to the min max optimization or max min optimization, similar to the adversarial training styles. So then by using this optimization, we can obtain the parameters that is robust.
Oh, I see. Thank you.
Okay.
All right.